So we are looking at titrations, but we're not looking at... Titrations can take up their own unit. What I'm doing is I'm going to apply titrations to the reaction math that we've been doing in here. So you'll see this idea of titrations show back up. Is it not coming? Is it doing it again? Yeah. Don't start a fire. Those of y'all at home, make sure you have the titration lecture slides up. You won't survive this lecture without them in front of you.
Oh, thanks.
All right, I got it searching again. It's going to find you now. Really, so super glad I pressed play already on the video. Oh, that was a good sign. Boom, a rooster. Okay. Hey, I do want to make y'all aware, though, we're going to run into several lectures where there aren't moments where I say, okay, now you try one. Only because there's so many different ways that these questions are asked. I feel like I'm doing you a disservice to have there be a straight 6-minute period where I'm not just showing you more examples. So this is one of several lectures where there's not going to be moments where we do an identical copy of a question so that you can practice. That's what Schoology will be for. I'm just going to spend the day just showing you basically every type of wording that there can be so that you can look back in your notes and have as solid of a guide as you can. But before we get into math, since we've been talking about reactions, I want to revisit particulates. Uh-oh, black marker gone. Right there. Because what we drew in Unit 1 were particulates based mostly around states of matter and the classification of matter. You showed like whether it was a mixture and what phase it was in. With the reactions that we're doing and the dissociation that we've practiced, you can show particulates in a slightly different way. So I just want you to be equipped with all of those skills. So it shows on the screen what we're going to be putting into our beakers. In the first beaker, it just says that we'll put water because, of course, that's what we would make most of our solutions in. We've drawn the particulate for water before. It's our Mickey Mouse, our H2O. But what was the way that I would draw it in particular to make sure that it wasn't ice? All right, float it around a little bit is kind of a weird way of saying it.
Not very organized.
Not very organized. Not floating around because then it becomes a vapor. All right? But, you know, I commonly will draw it like this where you can see that there is organization, but that it's not as organized as it could be, which kind of indicates that it's a liquid rolling around there. So anyways, this could be just our beaker of water. But then it wants us to dissolve, and I'm gonna draw a different beaker. My picture gets messy otherwise. Potassium iodide in there. All right, well, what happens if you add potassium iodide to water? No, it won't be a reaction. They dissociate. That was the perfect word. You made up for it right there. I like that. Yeah, hey, but how do I know that potassium iodide is soluble, though? Because the halogens are, except for just a few exceptions that I'm sure you have on the tip of your brain. But anyway, yeah, this is a soluble salt. So it will dissociate the way that you would expect it to. Hey, what's the ratio of ions here? 1 to 1. All right, the ratio would be 1 to 1. For every 1 potassium, there's 1 iodine. So if you were actually drawing a dissociation particulate on an FRQ, make sure your ratio is right because they're checking to see that it is. All right. Well, let's find another reactant that we could do in this reaction that we're tiptoeing toward. We're going to add, we're going to create a solution of lead 2 nitrate. What about him? What happens if you add him to water? Will he dissociate? Yes. How do you know he will? Nitrate's part of Big Daddy. He's bold, and he always dissociates. Hey, what's the mole ratio here? 1 to 2. So make sure that you draw it properly. For every one of these leads that you have, there's 2 of these nitrates. It's more common. It shows that the 2's holding a sword. Whoa. Well, it's 2 for every one, you see. All right, so then what if we mixed the beakers together? What if we poured the beakers into one another? What it would ultimately be is this reaction, right? All right, so if we were to prepare to do that, what would our products be? Well, it looks like it would make potassium nitrate alongside lead 2 iodide. Don't do that. The audible sigh. Do an internal sigh. What are the solubilities of my products? Aqueous, because nitrate's always aqueous.
Solid.
And solid, because that is a halogen that's pretty bad, right?
Oh, yeah.
Oh.
Argentina, Sri Lanka? Anybody? Anybody using that?
Wait,
No.
what's the Argentina?
That's with sulfates anyways. So, now, if we're going to draw the particulate after the reaction, it gets very interesting, especially if you balance the equation, because there would have to be a 2 there and a 2 there. Now, I don't care about the reactants, though, because once the reaction happens, we're only going to have the product. So let's see what's in the beaker. Oh, yeah, you can flip to the next slide. I'm sorry, but it's just... Oh, nope, you can't. You already did. Ha. I know. You're okay. You're smarter than me. Stop it.
You told me to do it.
I did. I told you I'm not sleeping well. Okay. Hey, which of the products do you think we should draw first?
The solid one.
Why the solid one?
Because it's always in my
Because that's what we want that solid to be organized and on the bottom. All right. So in our reaction chemistry, we can just draw it like this. All right. And
Which one do we do? The second to last.
I'm sorry.
Which one do we do to some? Which one do we draw like that on?
This is this one right here. This is a beaker of them mixed together. Yeah. All right. So we've got our solid lead 2 iodide that is not dissociating, all right, because of its solubility. But we've got our potassium nitrates up here. Hey, based on the number of lead 2 iodides I drew, how many potassiums must I draw right now? Be more 4, right? Because if you have 1 PbI2, you've got 2 potassiums. So if you've got 2 PbI2s, there'd be 2 potassiums. 4 potassiums, sorry. All right, it would be the number twice. All right, so there'd also, now it's going to get messy because I'm out of space, but you need how many nitrates also? 4, right? Because if you have 1 of PbI2, then you have 2 nitrates. So if you have 2 PbI2s, you have 4 nitrates.
I don't have room for four nitrates. The fourth nitrate spills.
All right, so hooray, but so it's bringing together your particulate skills while representing what's happening in the reaction.
Is that titration?
No,
No. Cool.
this is just a good spot to throw in this reminder.
Potassium and nitrate, would that be gaseous?
No, aqueous, totally in solution. So yeah, so you would want it to be, near the bottom. But if you're showing your solids in this form, then now it's obvious to the grader that you're showing something that's not solid there. So you wouldn't want it floating out of the beaker or whatnot. But Usually they'll provide you some of the drawing to have you draw it into instead of a blank sheet like my FRQs do. But I don't have the printing skills they do. Now, the only other thing that you could point out is what if you put in a non-electrolyte? So realize that something like sugar here that is a non-electrolyte is not going to dissociate. So if you're drawing the particulate of it, all right, like if you're making sugar water, you can put your water in there, all right, and it's going to be the sugar floating around in it because it will dissolve, but no dissociation.
What does that say?
Sugar. That's sugar. So anyways, so keep in mind that while you are really in the habit of just dissociating everything, that your covalent compounds are non-electrolytic. All right, let's change gears. You may have done a titration lab. A titration is the way to figure out the concentration, the molarity of an unknown. All right, you know what the substance is, you just don't know how strong it is. So what you can do is you can take something to neutralize it. Like if, let's say we have an acid and we don't know what the strength of the acid is. We just know it's hydrochloric. Well, what we could do is we could take a known base at a known concentration and slowly add to it. If you add some indicator, the colors, you know that the colors change as the pH changes. So what you can do is watch the colors change as you're adding the drops and find out at what point does the acid become neutralized. At what point is the hydrochloric acid no longer at a pH below 7? And then you can look at the amount of base at the known concentration that you had to add, and you can run a simple little calculation to find out what the molarity of the acid would have had to be. Now, if you didn't follow that, we have a whole titration unit coming up in probably early November. So we'll play with that. For today, I want to apply just some of the basic reaction math that we've been doing to a neutralization titration type reaction. So switch the slide. The steps for solving all of these are going to feel very stoichiometric in nature. And what I mean by that is our given has to be in moles. We'll always want to know moles of the unknown and then do a final conversion to something. The real challenge on the AP is that when you get to May, they know you've had the whole course. So that something at the end can be a huge amount of things. So we just want to practice as much as we can to encourage the idea of you knowing what to do after you go moles to moles. But really, when in doubt, and that's the other big piece of chemistry advice that I can give you today, is when in doubt, go to moles. If you ever run into a question, you're like, I don't even know where to start, convert to moles if you can. That's probably the first step if you don't know what to do. All right, so with that in mind, let's just jump into some, don't want to say random examples, but I'm going to try to give you a variety. Okay, so our first titration, all right, adding an acid to a base to make it safe, neutralize, is going to be sulfuric acid with sodium hydroxide. So let's go sulfuric acid with sodium hydroxide. It's a neutralization reaction, so predicting the products is extra easy because you know salt and water are coming. So it looks like we're going to have water, of course, and sodium sulfate. Balance the equation. Make sure you do stop me if at any point I write something that you don't understand. All right, so let's take a look at all of our data. There's quite a bit. It gives us 20 mils of the acid. So we've got 20 milliliters of sulfuric. and then 18.5 mils of the base. But it also tells us his molarity, because of course during a titration, you know all the information on one of your reactants. So we're using almost 1 molar of the sodium hydroxide. So one of the skills, or rather simple equations, calculations you're always going to want to have in your brain is the fact that when you're dealing with molarity, if moles is all that you're missing, what is the arithmetic you need to do to find moles? Just multiply molarity times liters. All right. Realize that algebraically, M times L equals moles. So with that assumption, we can run very quick calculations here without having to continuously rewrite that equation. So if I'm given volume and I'm giving molarity, it's the product of these two that will give you moles. Because as we said a moment ago, you have to start with moles of given. Now, what's the only issue I have with the way those are written? You cannot put milliliters into the molarity equation. So again, the conversion should be second nature to you. It's 3 slides to the left, or you can divide it by 1,000 if you want to do that in your calculator. All right? But really, it's 0.0185 times your molarity is going to give you your mole count. Do we have Aspen out there yet? All right, so let's get our first mole count from 2,5. Hey, 2,5, what is my mole count there?
So 0.014. That's wait.
Well, I haven't done it yet. I want to agree with you.
It's starting at 0. Wait, no. So then it's probably 0, 1, 3, 9.
What are we doing? We're doing 3 6 figs, so yeah, we'll go 1 3 9. All right, everybody all right? So what we have right now is we have moles of our known. As we said, from there, we want to go to moles of the unknown. We're trying to find out stuff about the acid that we're titrating. So that's our basic conversion that we want to do. Of course, the diagonals will match the units. And where will the values come from if moles is over moles? The coefficients. So my sodium hydroxide is 2. My acid there is 1. And then this can give me my mole count of the acid. So basically just dividing by 2. Everybody okay with the blue value?
No.
That's 6.5.
Yeah, it's fine. If you did you use like the original one?
Yeah, I probably did.
Okay.
Either way, we're far from that decimal. I think we'll be okay. Okay. Well, cool. So we've got moles of the unknown, and then it said, well, from there we can go to whatever it wants us to. Well, this question wants molarity. So what we're missing over here is molarity. And from here, it should be very simple. If we know moles and we know volume, how do we find molarity? Just divide. Molarity is moles divided by liters. So we'll take our moles and divide it by 0.02. We'll have somebody give us their answer. Cluster 2, seat 5. I swear. I swear. Check it out. Check it out. 2s and 5s. 2s and 5s. It's not rigged. It just hates her.
Is it still 3 centimeters?
Yes.
Okay, great. 0.348.
0.348. Molar. Which, of course, is moles per liter. Remember, I mentioned that you're going to see that show up quite a bit, but it means molar. Not too bad, right? All right, well, let's put a tiny twist on it. Go to our next problem dealing with barium hydroxide. All right, so let's start with a reaction. We've got barium hydroxide titrating with hydrochloric acid. Barium hydroxide and hydrochloric acid. Strong, strong is going to give us barium chloride and water. Right, we've got some balancing issues. We're going to need 2 of our acid.
Bless you.
Bless you. All right, let's take a look at the info that we've got. It's letting us know that there's 16.52 mils of our acid at 0.85 molar.
Thank you.
There's not like particles of stuff floating around in here, I promise. All right, and then for the barium hydroxide, it gives us 25 mils. Now, on this problem, I just want to say right up front, one of the most annoying things that can happen to you on the AP is when they give you too much information. It can really throw you if you don't have a good handle on your chemistry because you want a number to go everywhere. They don't do it very often, but in this case, that 25 mils is unnecessary to find grams. It doesn't want molarity this time. It just wants to do a simple mass conversion. So anyhow, I just want to warn you that you will need to read the problems carefully so that you don't try to find a use for numbers that are pointless. All right, well, there's all our info. We know that starting with moles of our given is important, so what do I want to do to those 2 numbers right there? Multiply them. All right, so make sure you do it correctly. Get a value while we head over to cluster 1, seat 5. Give us a mole count when you have it, please.
Uh, 14 point.
Did you convert your mils to liters?
Oh. .0140.
Yep, I like it. And now we've got moles of acid. All right. Of course, we want moles of our unknown, so let's turn that into moles of barium hydroxide. Make those diagonals match. Units. Moles over moles is going to request coefficients. The acid is 2. The base is 1. Everybody okay with my 702-ish number? Cool. So now in the last problem, it wanted molarity, so we just divided by the liters that it gave us, or the milliliters. All right, that's not what it wants this time. How will we get to grams?
Using average, like periodic.
Easy, right? We just want to convert to grams then. Moles to grams, been doing that for years. So let's go to grams of barium hydroxide from moles. We know that 1 mole is equal to periodic table grams. So I bet y'all are adding it up while I draw a card. Cluster 6. Uh-oh, Aspen's looking very promising. Seat 4. Have we been counting you as your regular seat, or are you 6'4"? Oh, very. Just kidding. Okay, Aspen, can you give me that molar mass, please? $2 million. Okay, hold on. Here, yell hers at me then.
Yeah, okay.
171.35.
Hey.
Yeah.
Oh, wait, no.
Whoa.
I thought you said y'all.
171. I said yell, but it's all right.
Because I forgot to let it touch.
Here, you know what? Go ahead and keep Aspen. All right, 171.35. Are we good there?
No, it's not 60 eligible.
Oh, no, for molar mass it is. Only 2 digits passed for all molar masses. Yeah. It's our new funky rule. Anyways, multiply and divide. And you are going to find out that your grams are about 1.20. Yes. Go hit second, then the 0, and then hit yes. And it'll undo all funkiness. We okay?
Yes. Okay, so what does this mean?
Okay, it was
I'm sorry?
What's that mean?
That's the amount of grams that was in the original barium hydroxide when the titration began.
getting better at this, by the way.
All right, so what about, here's a think about your answer question. But the work is far shorter. So we're doing a titration here, but we've got all the information on both of the reactants. So let's take a look. It looks like we're going to be putting hydrobromic acid with sodium hydroxide. Hey, look, they're all 1 oxidation states. Does that click in y'all's brain when you're writing it? You get excited when everything's a +1, -1? No? Y'all haven't gotten there yet? Well, you'll get there. Anyways, this means that the balancing is going to be very simple. What my brain tells me. All right? Because it'll be all 1s. Anyway. So let's look at the information that it gives us. For the acid, it tells us that we are at 25 mils of 0.625. And for the base, we're at 42 mils of 0.352. What? And look what the question's asking. Will the resulting solution be acidic or basic? Well, it's not supposed to be either, right? It's neutralization. We're supposed to end up with just salt water. But what kind of problem does this look like with the way the information's been presented?
Percent composition.
But I think you're thinking the wrong thing, the right thing, but you said the wrong thing. When you're given full information on both reactants.
Percent yield.
A limiting reactant problem. Percent yield requires an actual yield be given. Anyways, that was they almost impressed you people at home, but they missed it. Okay. Yeah, this is a limiting reactant problem. So let's take a look at what we would do here. All right, well, we don't have moles of anything, but we know how to find that. It's some simple multiplication. So let's multiply these together to get moles of base. So 0.025 times 0.625 to 3 sig figs is going to be 0.0156.
Or would you multiply?
To find moles, we always go molarity times liters. Ooh. All right, so let's find out the mole count of the other reactant. 0.042 times 0.352 to 3 sig figs is going to be 0.0148. Remember, the shortcut for limiting reactant is that if you know the mole count of your both reactants and you simply divide them by their coefficients, the smaller number can win right there. What are the coefficients? They're both 1, which means we can use these values to determine which one will be used up first. Which reactant's going to be used up first? The bases. So if the smaller number disappears, even though it's a neutralization reaction, will there be acid or base left over? Acid. So it's going to be acidic because this guy here is in excess and he's still going to be floating around in the beaker when it's all said and done. Now I know what you're thinking. Sir, can't you give us a harder one?
No.
What?
And I've absolutely got you.
Why would anyone ask that? So right. Oh, sorry. I said I was getting better.
So of course what FRQs like to do is drag skills into the same problem. So you've got to be able to read through the words and apply your abilities. So again, let's refocus. For those of y'all at home, this is the long dissociation equation that we're looking at. All right. Now, if we read through, the first thing that it's going to do is build a stock solution. It says that we're going to prepare a dichromate solution by dissolving potassium dichromate in water. But you'll see that there is no potassium anywhere to be found in the equation. It's because we're going to make a solution, and then from that solution, we're going to go do this reaction. So let's start by making our stock and carefully making sense of the words. It says in order to make the stock solution, it tells you the amount of grams that you're going to be putting into an amount of water. So from that, we can easily find everything that you've been trained to find. First off, we can't put if we want to find the molarity of our stock solution, we can't use grams. We need moles, just like every problem we've done so far today. So let's take that gram count that we're starting with, the 6.425 grams, and that's of my potassium dichromate. And let's get a mole count of him. So nothing should even really feel different yet because we're going to convert to moles. So we want to go to moles of the K2Cr2O7, make the bottom match, and I will need one of you to go and fetch that molar mass.
Fetch?
I need you to be a good girl. Is it strange? Don't do that again.
Kind of.
No, I'm deleting it. So we need the PT of K2Cr2O7. Uh-oh, cluster 6. Aspen, you're about to get... Oh, yeah, we don't have anybody in the cluster. Aspen, can you give me that number?
Is it 294.2? My calculator doesn't give me the other number.
Can somebody second that value?
I have 255.
Let's duke it
I
out.
got a lot of different calculations to pass through.
Right, I've got 294 twice. Can somebody third 294 then? Okay, good. So let's go for it. So let's solve. So 6.425 ultimately divided by 294.2 is what? Thanks. I'm gonna get a text tonight. Schoology message. Hey, guess what I got for that? I'm going to get a mole count of 0.02184.
We're going all over this many? Oh, yeah, because it's
All right, and this is going to be my moles of K2Cr2O4. Hey, how much water are we putting that in to make this stock solution?
Why is it 04? Why is it 04 not 7?
I'm sorry?
Yeah, it was 7.
Dichromate, you
The
put
04 instead of 7.
Oh. Sorry.
Or is it weird?
You looked at the smallest number I wrote up there. I'm very proud of you. We're dropping it into 800 milliliters of water. So we know to find the molarity, it's moles over liters. So we can very simply drop it into liters, which will be 0.8.
Wait, that's up what?
800 milliliters.
Oh, yeah.
Yeah, because look what we're doing. In order to make the stock, in order to get this given ion to start our titration, we are putting 6.425 grams of a salt that it's contained in into that much water. And it's going to build the stock solution for us.
Yeah, we're not even started with the test yet.
So just on the test all
All right, so I get a molarity then of 0.02730. Let's see if somebody can second that crazy number. 2730 molar. Is that okay? All right. You want to start a chemistry problem now?
Wait, what?
I'm just saying that that's just the first step. All right. So here's what it wants us to do, though. It wants us to take this stock solution that we made, all right, and it's dissociated. So now what's floating around in it? Cr2O7 plus 2 is floating around in it. So we're going to take a certain amount of it. It looks like we're going to take 0.02135 liters of our Cr2O7 minus. All right, that's the amount that we're starting with. So now we have a new given. So what do we need to convert it to right away? Moles. Now, you can get confused here. So watch. Here's the confusing part if there is one.
22.7.
Realize that molarity here is really moles per liter. So we already have this conversion directly set up for us because we're trying to go from liters to moles. So if I want to do this conversion factor as simply as I can, I know that for every 1 liter, there is 0.2730 moles.
I thought that was grams.
Sorry? So it's just this one conversion step. Remember, the whole point of our dimensional analysis is to have squares equal each other that are over one another. We know that our entire molarity equation tells us exactly this. That line in the unit is that denominator line. So it says that there's 0.02730 moles per liter. So if we have a certain amount of liters, then we can make the assumption that if we were to have 1 whole liter, it would equal that amount, which of course is going to make the units do what we want them to do, because liters will cancel out and we'll be left with an exact amount of moles.
Wait, what? Liters?
That's the basis of dimensional analysis. If something's on top and on bottom, they cancel out. That's why the grids work in the first place. So by running this, we will get our starting moles of our dichromate. So do I still have the right number in here? 0.02135 times 0.02730. This is what always happens in your dimensional analysis, the crossing out. If a unit is on top and on bottom, it disappears. That's the reason that we always drag the units to the diagonal, right?
But you still did the math.
Yeah. Everything else is the same. I'm not changing anything crazy on you.
Just never do that again.
Why would you put
I know, like,
I'm getting a mole count of 0.000.
5828555.
Oh, I used different things.
5829. And that's going to be moles of my dichromate, hooray. Just the starting value. I mean, both of these values have 4 sig figs. Everything that we've messed with has had 4 sig figs. Of course, conversion factors never play into sig figs. All right? But what does this want? It wants concentration of Fe2. All right, well, we need... I'm sorry? Yeah, we haven't answered the question yet. All we've done is we've taken moles of our given, and gone to moles, and now we have moles of given, so now we need moles of unknown. So we can directly convert this to moles of what it wants. Now look, this is asking for moles of the iron 2, is what the end game is here. I'll tell you who dies. So let's crisscross the units so that they cancel out, but I'm not allowed to say that, apparently. All right, we're doing all the same steps from the previous problems, guys. It's just we had to make this stock solution using a step you're familiar with. We converted to moles of our known, like we've done in 3 previous problems. Now we're going to moles of the unknown using coefficients again. And look, you have a balanced equation up here. It's a 6-to-1 ratio if you use the coefficients. And this will give us our mole count
On the test.
of the unknown. Oh no. No, it's not. That's why this is not the last step. This will give us a mole count of 0.0035. Oh, wait, where it's 4 sig figs? Never mind. 003497. And that's moles of the unknown, iron 2. And now, just like we've done in every problem we've done today, there's one more thing it wants. It wants the concentration.
So the
Moles divided by liters gives you molarity, which is concentration, divided by that concentration of liters, which is ultimately 0.25, will give you your answer.
will you give us a
ran
balanced
out of
equation,
time.
or do we have to also do that?
No, I mean, I purposely gave you this one balanced for a reason, because the problem was
Oh, thank you
intense.
so much.
All right?
Appreciate that.
Your answer should be 0.01399.
Wait, but when we get like on the test, will you have a balance it, or will it already be balanced?
It depends.
Are you ever going to do this long test?
The test would be shorter if I did. Let me write the answer for all the people at home that didn't hear me dictate it. 0, 1, 3.
Dude, all for this answer, I would have guessed on the test. You all this, I promise you I would have guessed.
Hi.